Hello everyone and welcome to this lecture. In the last lecture or maybe last to last lecture we had started discussion on expander graphs, right? So these are the graphs which are very sparse but are well connected. Earlier the existence of such graphs was in doubt, but then mathematicians, they come up with a nice construction of expander graphs. So we will see what was the first construction of expander graphs, and then we will move ahead with the best possible expanders, or optimal expander, those we call Ramanujan graphs. Okay, so let us go ahead with the discussion of the last lecture. I remember I asked you this question. Think about constructing some expander graphs, basically family of graphs where every body is sparse but well connected, the family of actually d-regular graphs, because we are considering only here d-regular case because they are sparse graphs, okay, for fixed degree, okay, and we are growing, we are increasing n, okay, and then we want to see the behavior, okay, great. So the first construction of the first explicit construction of the expanders was given in 1973 by Margulis. So what is this construction? This construction is you pick any number m, okay, then take the subset of numbers from 1 to up to m minus 1, okay, this set, and the Cartesian product of this set with itself will be actually it will be giving you pairs, right? These pairs are now vertices. So suppose xy is one such vertex. This xy is then have edges with 8 other vertices, and these vertices are listed here, x plus minus y comma y. So in this way there are 8 vertices. So this graph is 8 regular. Remember I also mentioned that here we can take the multiple edges also, self loop also, but in total this is a regular graph. So every vertex has 8 incident edges, okay. Now Margulis actually proved that this graph for any m, the second largest eigenvalue lambda 2 will be strictly lesser than 8. Remember lambda 2, if it is equal to the degree, here the degree is 8, right? If lambda 2 is equal to degree, that means graph is disconnected, right? Lambda 2 is strictly lesser than 8, that means for any number, you whatever m it is, it will always remain connected, okay. So let me actually recall the same expression given by Alone and Millman. So expression was this, right? So your expansion coefficient was what? So it was always less or equal to, let me write this quantity here, 2d into d minus 1, where d is your degree, and it is always greater or equal to d minus lambda 2 divided by 2, okay. If you see on both hand side, sorry, this is lambda 2, okay. If you see both hand side, there is a quantity d minus lambda 2. If lambda 2 is strictly lesser than d, that means hg is always positive. This in a way tells that graph is connected. Very good, okay. And oh, by the way, Margulis got Fields Medal in 1978, and it was the ceremony was postponed due to some visa constraint, I guess, and he got recently Abel Prize, which the ceremony was postponed due to COVID. So these are kind of coincidence, okay. Very good. So so this is one example of the construction by Margulis, okay. So where m equal to 3, okay. Now there will be 9 vertices, and each vertex has degree 8, and the edges are actually with this rule, okay. Very good. And he has proved that the lambda 2 is always strictly lesser than 8. Then after some years, Geber and Galil actually modified this. They have improved on this. So they said that rather than connecting this xy to earlier vertices, connect to these new vertices. Again the graph is 8 regular, but lambda 2 is much lesser than the earlier one. So lambda 2 here is less or equal to 7.071, okay. This implies what? This is a better expander than the earlier one. it has better expansion ratio than other one. Okay, so remember, lesser the lambda 2, better is the connectivity. Okay, very good. So we want Hg to be bigger, that means we want lambda to be smaller, or we want the spectral gap to be larger. So all these are the same things. Okay, but now what? If you see, so always we are desiring for what? Can we reduce the lambda to further and further? Okay, but there is some bad news. Okay, soon I will tell you what that bad news. But before that, let me make a background for that bad news. There is a limit to which you can actually reduce this lambda 2. Okay, if you see it, so let me actually show you one intuition behind it. Okay, so you cannot reduce lambda 2 arbitrary. Okay, so let's suppose lambda is actually some eigenvalue which is actually largest in modulus other than d. Okay, so lambda is some eigenvalue. So largest eigenvalue is what? D, right? And so largest modulus is d. In case of bipartites, then minus d is also eigenvalue. But you think that the eigenvalue which has the largest modulus other than d, suppose lambda is this one. Okay, so basically I can actually write this is nothing but minimum of lambda 2, so lambda, so this will actually suffice. Suppose this is this quantity. Okay, now what? If you see this matrix, suppose A is adjacency matrix of some d regular graph. Okay, suppose A is adjacency matrix, what will this equation give? A square will tell you what? Every entry of A square will tell you the number of walks of length 2 between I and j, right? So if you consider the diagonal entries, it tells you the number of closed walk of length 2, which is nothing but degree. So basically, if you talk about the trace of this, this is nothing but d plus d plus d. How many times is this? N times d. So it is n into d. Okay, but the same thing, these things, by spectral theorem we can also write in terms of what? Eigenvalues, right? How we can write? So we can write this lambda 1 square plus lambda 2 square up to lambda n square. Okay, lambda n square. Now you see that lambda 1 is what? Lambda 1 is equal to d, right? So this is d square, and this is d square, and actually, so this quantity is, okay, let me first write it same, okay, plus d. Now you see that, so lambda is actually, sorry, it is not minimum, I think it should be maximum. Sorry about this. So it's a max of this. Okay, now you see that lambda, I can write this equation as this, right? D square plus out of all these lambda 2 up to lambda n minus the mod of lambda. So lambda is the maximum modulus. Okay, so actually I can write this n minus 1 times lambda square. Correct, right? So this, now if you see that inequality, so basically I can write this, so nd is nothing but less or equal to this. Now you just see how can actually we write. So this is just manipulation of sum here and there. Okay, so this is d into n minus d divided by n minus 1. Very good. So this is lambda square. So lambda, so that means what? That means what? If you see carefully here, it is actually, so yeah, so lambda is always greater or equal to square root of d, and then there is some term which goes to 0 when n is very large, right? When n is very, so it is actually 1 minus d by something. So it is actually something here. So let me write, so 1 minus some constant here. You can write some constant which goes to 0 when n. So basically lambda is always when n is very large. So basically when n goes to infinity, okay, lambda is always greater than, lambda is always greater or equal to square root of d times some constant number, maybe some constant number. Okay, so you cannot arbitrarily decrease lambda. Okay, there is a limit to it. Okay, in fact there is a more bad news, and this was given by these two mathematicians. Okay, earlier Alone and Millman has given a very great news where we can write the expansion ratio in terms of eigenvalues. Now this is slightly bad news, that you cannot arbitrarily decrease lambda 2. Okay, in fact you cannot arbitrarily decrease the largest modulus of eigenvalues other than D. Okay, and this is the exact point where the Ramanujan graphs are defined. So what are the Ramanujan graphs? The Ramanujan graphs are the graphs for which this lambda is less or equal to 2 square root of D minus 1. So what are the examples of Ramanujan graphs? Believe me, you have already seen many examples of Ramanujan graphs. We will shortly see. Okay, very good. So Ramanujan graphs are for very large n, basically n tends to infinity. You cannot decrease lambda further, and this is the limit. Okay, the graphs which achieve these limits are the best possible expanders. We call them Ramanujan graphs. Shortly we will see why we call them Ramanujan graph. The spectral gap for these are super high. Okay, the best possible spectral gap for this, and for such graph, if you see that lambda is the minimum, right? The lambda is minimum, right? So the random walk is fastest. Random walk is super fast. Okay, very good. So great. Then now let us move ahead with some examples of Ramanujan graphs. Okay, so I promise that you have already seen many examples. Complete graphs are Ramanujan. Complete graphs are Ramanujan. So this is easy to see, right? I mean, the eigenvalues of complete graphs are what? And then -1, so on. The mod is 1 here, and this is always less or equal to, if you see that, what is that quantity? Square root of the 2 square root of D minus 1, right? So this will be always coming out to be for different degrees of complete graph. Okay, so n minus 1, and again you are doing -1. Okay, anyway, so very good. And similarly, you can actually verify that complete bipartite graph is also Ramanujan graph. Peterson graph is also Ramanujan graph. You just see the eigenvalues. Peterson graph is indeed, I mean, a strong diagonal graph, and you can immediately see the eigenvalues based on those parameters. So it is easy to verify this is also Ramanujan graph. Okay, very good. Yeah, lambda is actually 2, so the degree is actually 3 here, so you can easily verify. Very good. Now, yeah, this graph, this we have seen last lecture, right, when we were giving a brief introduction about expanders. So this graph is also Ramanujan graph. By the way, I have taken this, I think this graph I have taken from a note from Peter Sarnak, and who is actually the first one, along with 2 other mathematicians, to give first explicit construction of Ramanujan graphs. Okay, very good. So yeah, now I told you that there are many graphs which are Ramanujan graphs, right? But explicit construction of Ramanujan graph family, okay, basically we have to make a family where every member is Ramanujan graph, and this has to be again D regular case, D regular where D is fixed. This is a challenging task. This is a hugely challenging task. Okay, and and that's why actually I have just made use of slide, because the proofs and everything are slightly advanced, so I have ignored them for this, because this is an introduction to algebraic graph theory. Maybe the advanced version of it will take these things into account. Okay, the first construction was given by Lubotsky, Phillips and Sarnak, okay, in 1988, okay, and this we call LPS construction. Okay, so they actually prove that there exists D regular Ramanujan graphs when D minus 1 is a prime number, and in order to construct such graphs, they have made use of the conjecture given by Ramanujan, which is now known as Ramanujan-Peterson conjecture, and then in honor of Ramanujan, they have named these graphs as Ramanujan graphs. Okay, very good. And later, few years later, Margulis actually generalized this result. He said that, he actually proven that there exists D regular Ramanujan graphs when D minus 1 is a prime power. Okay, earlier it was just prime number, now they are prime power. Very good. Okay, great. And this is one beautiful picture of a Ramanujan graphs on having a degree 6. Okay, this is a 6 regular Ramanujan graph, and this is LPS example. Okay, LPS by LPS construction by Lubotsky, Phillips and Sarnak. Very good. And very recently, Srivastav, Marcus and Spillman actually shows there exists infinite sequence of d-regular bipartite Ramanujan graphs for every d greater or equal to 3. By the way, they have actually solved a conjecture given by Billu and Lineal on two-lift. We will see two-lift concept in the next lecture. So they have proven this conjecture for bipartite case, and by proving this, they have shown that there exists infinitely many d-regular bipartite Ramanujan graphs. Okay, very interesting one. Okay, this is actually very recent result, and then actually later they have actually shown that for every degree and every number of vertices there exist Ramanujan graphs. Very elegant result on this. And later Michael B. Cohen actually show how to construct these graphs in polynomial type. Okay, very good, but there is still a challenge lying ahead. Okay, the conjecture given by Billu and Lineal is still open for non-bipartite case. Okay, so it is still unproven, that it is still open problem that there exist infinitely many d-regular non-bipartite Ramanujan graphs for d greater or equal to 3. Okay, very good. So and by the way, so now talking about the applications of Ramanujan graphs in the lecture, last lecture, I have listed down many applications. Okay, all these applications, maybe more than that. Okay, the Ramanujan graphs are highly applicable. Okay, because these are the best possible expanders, right? These are the best possible expanders, and these were the applications of expanders. So if we are getting the best possible expander, so there are many use of this. Okay, very good. So now, but I also said this, I mean, coming up with explicit construction of Ramanujan graphs is extremely challenging problem. A family of Ramanujan graph, explicit family of Ramanujan graphs is extremely challenging. Okay, explicit here means you know that which vertex is actually have edges with which other vertices. Okay, fortunately life is slightly easier for us since 2003, when Friedman actually proved that if you construct the regular graphs randomly, d-regular graphs randomly, then almost surely they tends to be bipartite. They tends to be Ramanujan graphs when n is large enough. So for a fixed degree and actually greater than 0, the probability that that eigenvalue, the largest in modulus other than b, is always less or equal to this quantity, the barrier you can say, plus rather than threshold, plus epsilon. This probability tends to one as n goes to infinity. Okay, so a random d-regular graph is asymptotically and Ramanujan graphs. And by the way, constructing regular random graphs is not that difficult as compared to constructing the explicit construction, the explicit Ramanujan graphs. Okay, yeah, of course, I mean, we for different purpose we actually prefer the explicit construction because we know that which vertex is having connection with other vertices. Okay, so anyway, but this theorem is also very elegant. Okay, so many works are actually based on this theorem. Okay, so very good. So I hope you enjoyed this very brief overview of Ramanujan graph. Okay, in the next lecture we will try to give a try to construct Ramanujan graphs or maybe expander graphs, some techniques which might give us some Ramanujan graphs or at least some good expanders. Okay, stay tuned till the next lecture, and thank you very much.